Hey everyone, in this video we are going to talk about the classic stone game problem and walk through a dynamic programming solution with a runtime of O(n)². This is a fun and clever problem where two players, Alice and Bob, take turns picking piles of stones, trying to maximize their own score. But that's not all. At the end, we also explore how this problem can be solved in a constant time. Let's dive in and explore the problem. Alice and Bob are playing a competitive game with piles of stones arranged in a row. Each pile contains a specific number of stones. In this game, we have an even number of piles and in total an odd number of stones. In the first example, we have 4 piles. In the first pile, we have 5 stones. In the second pile, we have 3 stones. In the third pile, we have 4 stones. And in the last pile, we have 5 stones. Now both players take turns picking a pile. On each turn, a player can only take the leftmost pile or the rightmost pile. Alice always goes first and both players are extremely smart. They always play optimally, meaning they'll make the best move for themselves at every step. The goal of the game is to collect more stones than your opponent. In this problem, we have to determine whether Alice can win this game or not. Now let's analyze the dynamic programming solution. First, we use a dynamic programming solution with a O(n)² time complexity and the O(n) space complexity. We calculate the optimal outcomes for all possible lengths of subarrays and eventually look at the full array. Later, we'll see how to optimize this to a constant time and space complexity solution. So the idea is that we create a dynamic programming array where the entry at position I represents the difference in stones between Alice and Bob. So the goal is to determine if Alice can secure a positive difference, that she has at the end more stones than Bob, and the solution will stand at the first position, so at index 0. This is the code, and I show you this with this example of input. So these are the piles, and ignore the fact that the sum of the stones is not odd. The sum of these stones is even, but for this solution it doesn't matter. To start, we initialize the dynamic programming array. Each value at index I matches the number of stones in the corresponding pile, because for subarrays of length 1, Alice can simply take the pile. In this section, we calculate the dynamic programming values for all possible subarray lengths starting from 2 and going up to the full length of the array. For each subarray, the current player chooses the better option, taking either the leftmost or the rightmost pile, and then leaving the rest for the opponent to play optimally. Let's begin with the subarrays of length 2. So we now watch at all subarrays of length 2. So we had the input of piles 7, 6, 4, and 5, and all subarrays of length 2 are 7, 6, 6, 4, and 4, 5. And our goal is to analyze them with the following formula. In this line, you can see we choose the maximum of these two parts here, and this is the important part here. We use this to determine the advantage that Alice can make. So let's look at this case where we analyze the subarray with just 7 and 6. So in this case, the length is 2 and our I is for the first case 0 because our subarray starts at index 0, this one here. In this case here, the starting point is at index 1 and I is 1 in this case. So what we are going to do is we calculate I and j, and I represents the starting point and j the endpoint of the subarray with the given length. And this statement right here represents the solution if Alice picks the leftmost pile and the other the rightmost pile, this one here. And we want the optimum here, therefore we pick the maximum. So the core of this algorithm is the max statement, which represents the two decisions Alice can make on her turn. She can either pick the leftmost pile or the rightmost pile. And let's break this down in detail. In the first part of the max statement, Alice chooses the leftmost pile, and if she picks it, she adds the stones in that pile in her total. However, we must then subtract the optimal solution for Bob, who will play next in the remaining subarray. Why subtract? Because we are calculating the difference in stones between Alice and Bob, and after Alice's turn, Bob gets to make his best move. The second part of the max statement represents Alice's decision to take the rightmost pile. In this case, Alice adds the stone from that rightmost pile to her total, but again we subtract the optimal solution for Bob, who will now play on the remaining subarray without the rightmost pile. And finally, the max function compares these two choices, taking the leftmost pile versus taking the rightmost pile, and the result is the better option for Alice, maximizing her advantage. And this process is repeated for every possible subarray until we calculate the result for the entire array. So what we did here, we calculated the new values for the DP array at index 0, at index 1, and at index 2. And if we put I and j in our max function, in our max statement, we get an advantage of 1 at index 0 because she can start with the 7 and Bob's picks the 6, and therefore she has an advantage of 1. The same for this subarray. She can start with the 6 and Bob's picks the 4, and therefore she has an advantage of 2. And with the last one, she also gets an advantage of 1 because she can start with the 5. And now we update our DP array and get the new values. This was the DP array before. And if we update the values, we get this DP array. And now we can go on with the subarrays of length 3. And if we go on with the subarrays of length 3, we now inspect this subarray and this subarray, and we are working with the values of the DP array right here. And I is now 0 and j is 2 because this is the starting point and this is the end point. And if we now put the values I and j in our max statement right here, we get an advantage of 5 now for Alice, because if we inspect this subarray right here, Alice can start with the 7 and Bob picks the 6 and she gets the 4 again, and she has a total of 11 and Bob has a total of 6, and therefore she has an advantage of 5. And if we do this with the other subarray, we also get an advantage of 5 because she can start with the 6 and Bob picks the 5 and she gets the 4, and therefore she has a total of 10 and Bob has a total of 5, and therefore we have a difference of 5. And what we now did here is calculated the new values for our DP array at index 0 and at index 1 for the length 3. And the new values are 5, 5. So we update this array right here and the values at this point to 5, 5. And this is our new DP array. Now we can go on with the full length with length 4. And we just update one index. We update the value at index 0 for the entire array with I 0 and j 3. And if we put I and j in our formula with the max statement, we get an advantage of 2 overall. And this means if Alice starts, she gets an advantage of 2 for the entire game, and therefore she can win this game with 2 more stones than Bob. If you now simulate this with the original piles, she can start with the 7 and Bob chooses the 6, and therefore she continues with the 5 and Bob gets at the end the 4. And overall she has a total of 12, 7 plus 5, and Bob has a total of 10, and therefore she has an advantage of 2 and she wins the game. And we calculated this with the dynamic programming solution, and the runtime complexity of this solution is O of n squared, and the space complexity is O of n because we just had one array and we updated this array where we just calculated the advantages for the different lengths. So far, we've walked through the dynamic programming solution, which uses O of n squared time and O of n space. While this approach works and provides the correct result, it turns out it's not necessarily to go through all this complexity. There is a much simpler way to solve this problem. In fact, we don't even need to calculate anything. Under the given rules that there are an even number of piles and the total of stones is odd, Alice will always win if both players play optimally. Why? Because Alice can always control the game and can ensure she collects more stones than Bob. This means we can simply return true for any valid input, as Alice is guaranteed to win. I'll explain in a second why. Okay, now let's see how the constant time solution works. So Alice and Bob are two characters. I'm gonna represent them with different colors. I'm gonna pick pink or whatever this color is for Alice and green for Bob. Now the idea is that we have an even number of piles arranged in a row containing stones, and the sum of all stones in a row is odd, and we will see in a second why that's important. Each turn the player takes the entire pile of stones either from the beginning or from the end, and both players, Alice and Bob, play optimally. Now let's inspect the case where we only have two piles. Assume you have two piles, 3 and 5. So the first pile has 3 stones and the second pile has 5 stones. And since Alice starts, she can choose which pile she takes. Of course, she picks the pile with a greater amount of stones, in this case 5. Because remember, the piles cannot have the same amount of stones since the total number of stones must be odd. Let's watch the next case where we have 4 piles. Now there are several options here, but we know there's one path where Alice wins the game. Assume we have the following piles. Let's start with 6, followed by 100, 2 and 5. So we have 4 piles here, and if we sum up the stones, we get an odd number, so everything is fine. Now the game starts and Alice can choose between 6 and 5. In a greedy algorithm, she would choose 6 because 6 is greater than 5. But in this case, this is not optimally because she will reveal the 100 to Bob and Bob wins. Therefore, in this scenario, she would start with the 5 to get to the 100. So assume she picks the 5. In the next round, Bob can now choose between 6 or 2. But either way, it doesn't matter which he picks. He will always lose against Alice because Alice gets to the 100. Now there are 2 pairs here, a green one and a pink one, and we know one is greater than the other because they cannot be the same, because if they are the same, this will implicate that there are even amount of stones, but there are an odd number of stones here, so one pair must be greater than the other. And since Alice starts, she can choose and control the game which pair she gets. Does she get the greater pair? And since they play optimally and Alice starts, we can assume that Alice always wins because she always picks the greater pair. Now I don't want to drag this out unnecessarily. If you're interested in a mathematical proof, feel free to write it in the comments, and I publish a video as well about it. That's it, we got 2 solutions for the same problem, one more efficient than the other, but probably we can solve more problems with the dynamic programming solution and get more information from it. There are other parts for the stone game problem on LeetCode, and if you want a solution for the other problems, please write it in the comments. Nevertheless, we are done with this video, and I wish you all happy new year, and thanks for 200 subs, and we'll see you next time.